So today we're going to take our idea of graphing y equals mx plus b, and we're going to continue with that, but in a system. And a system just means more than one. So basically, we're just going to be graphing two lines on top of each other and trying to figure out where they meet. I'll get to why we're doing this in a second, but let's just do a quick review of graphing lines. So if I was going to graph this top line, I'm going to get that y-intercept of -5. I'm going to come down to -5. I'm going to put a point right there. And then I'm going to use my slope to go rise of 2 and a run of 3 and a rise of 2 and a run of 3. And I would get that line. There's our y-intercept, up 2 over 3, up 2 over 3. Now what we're going to do is we're going to graph a second line right on the same piece of graph paper. This time the y-intercept is going to be up at 2, and my negative slope is going to take it down 1 and run 2. Rise of -1, run of 2, rise of -1, run of 2, and when I graph that line, it's going to look like that. And then when we're talking about a solution, it's where do they meet? So in this particular case, the solution, would be the point 6, -1. So graph one line, graph the other, where do they meet? Really important that you're accurate, really important that you use a straight edge or a ruler to make sure that you can find that intersection point. So before we go any further, I just want to give you a quick heads up of like, where does this get used? And it's really very important in the business world. So basically what I've got on here is a switch, and I'm talking about like the Mario Kart 8 game, sales and costs. And so there's going to be a new game, or when this Mario Kart 8, Deluxe was new. Basically, they're going to put somebody on programming that, and somebody is going to develop that game over maybe a year. And then they're going to start, once they have it all set, they're going to start selling it. So what you have on this graph is the sales and the cost. So one of these lines represents the sales, the money coming in, how much money that Nintendo is getting from the game. And the other one is going to be the cost, their expenditures, because they're going to be spending money to pay people and to pay for advertising and all of that. So when you look at the two lines, my first question is, can you tell which one is the money coming in, sales, and which one is that money going out, costs? So what I immediately notice is that their y-intercepts are different. Their slopes are different too. But notice that this one starts that when 0 are sold, you have 0. And then as more and more units are sold, more games, notice that this one is going up. Did you guess that that one is the sale? So when you've sold 0, you've made 0. Now look at the y-intercept here. When you've sold 0, there's like $3 million here. What is that $3 million? Well, this line is going to keep going up as well. Not as steep of a slope, but that blue line is going to be your cost, your expenses is another word for that. So but when they hadn't even sold their first unit, they'd already spent $3 million on development and advertisement. Now, the money, is still going to go up based on working still on that game and fixing it or whatever. So that's why the expenses are still going up. But if you notice right here, the two meet. And when the expenses, the money that they cost had already kind of gone above the sales, at this point it goes below. So at this point, you start making more money than you spend. So right in here, this is where we start seeing profit. And that point where they meet is called the break-even point. And we've actually talked about this before earlier on in our last unit when we were solving equations. So in order to do this, that's just to kind of give you an idea of how important it is to be able to see where two lines meet or two different things like costs and sales. Let's go back to the theory and just go back to kind of practicing. So basically, a system of linear equations, also known as a linear system, is two or more equations that use the same variables and they're solved simultaneously. That means that we're putting them on the same graph. We're solving them together. The solution is the set the ordered pair that solves both. It's where the two lines meet. And the x and y coordinates of that point will make both functions, both equations true. So this is what we're going to do. The first thing is we need the equation to be in the form that's easy to graph, y equals mx plus b. We'll talk a little bit at the end about what if it isn't. You graph both on the same coordinate system using a straight edge and graph paper. You kind of estimate what you think the point of intersection is, and then you're going to check it by putting those numbers, the x and y, in both of the equations to see if it's true. Kind of like the check we did back in Unit 3. There is one done in your book on page 234. I just want to draw your attention to that there is one done out, but I'm actually going to do another one. I'd rather do it with you, so I'm going to make up a few. But page 234, if you need to kind of review one, there is one done in your book. So here we go. We're going to solve this system of linear equations, y equals mx plus b, and we're going to see where they meet. So remember, we're going to take that point and we're going to start by putting it on the -4. That's our y-intercept. And then I'm going to start at that point and I'm going to rise 2 and run 3. And then I'm going to pick up my ruler. I would even kind of do it again, I have to admit, just in case you miscount. It never hurts to do one more to make sure they all line up. And then we're going to draw that line in, and you'll see the blue line right here. Let me go back and just remind you on the other line, we're going to take that -5 this time. And when we don't see a number in front of that variable, there's no coefficient, it's the invisible 1. So we're going to rise 1 and run 1. So I'm going to rise 1 and run 1, and then I'm going to rise 1 and run 1. And what I advise you to do is sometimes it helps if you kind of keep going until you hit where that other line is, and that will be real. Oops, I didn't grab one. You keep going, and then look, see how those overlap? I can see sort of that intersection point. I'm going to pick up my ruler and draw that line in, and that's kind of what we're looking at. So what is the point of intersection? See, it's right here with the overlap, and it would be 3, -2. That's my point of intersection. Now, these lines are really close together, and it would be easy to wiggle and maybe not be able to see where they meet as readily as the last one I did with you. So we're going to check it. And remember, back when we were checking equations, we would substitute in and do the math. So I'm going to put the 3 in for x, but this time I'm going to put the -2 in for y. And I'm going to see, I'm going to use, my PEMDAS, I'm going to multiply and subtract. I'm going to see if I get that answer. So right here, here's my 2/3. I'm going to put the 3 in for x. I'm going to put the -2 in for y, and I'm going to do my math. When I'm multiplying fractions, I multiply at the tops. You don't need a common denominator. So this is 6 over 3. 2 times 3 is 6. 3 times 1 is 3. And when I take 6 divided by 3, I'm going to get 2. And then 2 minus 4 is -2, and I am happy because that point did work, so it means it's on that line. Now I have to do the bottom one. So I'm going to put the 3 in for x, and I'm going to put the -2 in for y, and that's what you're going to see right here. And then I do the math. This one's easy. 3 minus 5, is it -2? It is. And since that point worked in both equations, I do have the intersection point. It is the solution to the system of equations. That's the math speak for what we're doing. So there's another way that we don't have to graph. There could be a kind of a backwards question. Is this point 0,5 a solution of the system? And you don't have to get the graph paper out, and you don't have to graph both and see where they meet. You can just basically do the check that we just did. So you can put the 0 in for x in the top equation and the 5 in for the y, and does the math work? And do the same in the bottom to see if it works there as well. So if I look at that top one, the biggest mistake is to put them in the wrong spot, So the x coordinate is your first one, goes in for x, the y is your second. And then I do the math. I multiply, I get 0, because -2 times 0 is 0, and 0 plus 5 is 5. So that 0,5 is a point on this line. Is it also a point on this line? Well, I'm going to put the 0 in for x and the 5 in for y in the second equation. multiply 3 times 0. I love that because that's 0. And 0 plus 1 is 1, and that's a big fail. So no, this is not a solution to this system. It is a point on the first line. It's not a point on the second line, so that's a big no. Let's do that again with a different system. Same point. I'm going to put 0 in for x and 5 in for y. That works. Okay, so definitely on that line. I'm going to put 0 in for x here and 5 in for y, and does it work there? Negative 3 times 0 is 0. Add the 5, and it works there. So this is a yes because it worked. It solved both equations. That 0, 5 is a solution to that system. So you can kind of see a no, and you can kind of see a yes there. So now let's talk about two weirdos. And those you might remember further back. They're the idea of no solution and infinitely many. So we're going to find that you could have two lines that never meet. They're called parallel, kind of like train tracks. So if that situation happens, there is no solution. They're never going to cross. So that would be an example of a no solution. The other one that's a little weird is, what if the two equations that are given to you are the same line? They lie right on top of each other. They're called coincidence line. If that happens, every point on one line is on every point of the other line. So that's called an infinitely many, kind of like that identity idea from the past. So basically on page 236, they're showing you right here, if you see these two y equals mx plus b, and they're plotting them. So there's the y-intercept of 1, and they're going up 2 over 1. And then there's the y-intercept of negative 3, where my cursor is. And they're going up 2 over 1. And notice that they're always moving the same distance away from each other. Because of having the same slope, they're always rising 2 and running 1, so that they're going to be parallel. So lines with the same slope but different y-intercepts will be parallel. They'll never cross each other. So here's an example of a no solution, and that's because the lines are parallel. Now, how do you see like the same line? Like, are they really going to give you like y equals 2x plus 1 and y equals 2x plus 1 and ask you what the solution is? And you're like, well, they're the same. So what they're going to do is sometimes in life, the equations can come and you can't really see that they're the same line. So you have to transform, you have to move things around so that the y is by itself. So if you'll notice over here, this one is easy. This one we could go and we could plot our y-intercept and use our slope to move, but things don't look right here because the y isn't by himself. So to get the y by itself, this x is going to have to move to the other side of the equation. And when we go to opposite sides, we do opposite operations. So I'm not going to add x, I'm going to subtract x. And you might remember this from our unit 3, that we were doing that when we had a variable on both sides. Now, when I subtract x here, this is a 0 pair, leaving y, and these guys are not like terms, so they are going to stay apart. And I'm going to write them in the right order. I'm going to put the negative x in front of the 4 so that it's in y equals mx plus b. Now, remember that this guy is the negative 1, the invisible negative 1. And now I'm able to graph both of these and see what's going on. So sometimes our lines might need to be fixed so that y's by themselves before we start. So now I could go ahead and graph these two, and I'm going to just show you that. I would y-intercept of 4 and down 1 over 1, y-intercept of 1 up 2 over 1, and the two lines would look like this. So here is my, let's see, 1, I'm a little bit off there, but up 2 over 1. And then the other one is 4 down 1 over 1, and you see they're meeting at 1, 3. And if I put the 1 in for x and the 3 in for y, it works in the top equation, the bottom equation, and the top equation. So that's just an idea of transforming. So let's just do a couple more, just transforming there. So if I look at this one, right, see how the y isn't by himself? So we don't have the slope yet until this guy is on the other side. Y has to be by himself. So to undo this, we're going to subtract x. Oops, sorry. I always have that problem with my mouse. So we're going to subtract x from both sides. This is going to make the 0 pair. And over here, they're not buddies, so they're going to stay apart. So I'm going to put the negative x in front of the negative 5, so it's in the right order. And now I've got y equals m, which would be the negative 1, x plus b, which would be the negative 5. Ooh, this one's looking a little more complicated, right? So the y is hiding in here. So this 2x has to move. So the opposite of adding 2x would be to subtract 2x. Here's my 0 pair. And I'm left with a 3x on the left and a negative 2x plus 9 on the right. And this time, darn, that 3 is still not, the y is still not by itself. I need to undo multiplying by 3. The opposite of multiplying by 3 is to divide by 3, and everybody gets divided by 3. 3 divided by 3 is 1. That's how we got the 1y. And here's our rise over our run. And 9 divided by 3 is 3. And boom, we're ready to go ahead and possibly graph that one. So just notice on page 236, number 5, they've done one like that. See, the y isn't by itself. This one's great, ready to go. But here I have to add 3 to both sides before I can graph it. And if you notice, when they add the 3, they've got the identical line, y equals 2x plus 1 and y equals 2x plus 1. It's the same line. So this is an example of infinitely many. Every point on one line is on the other line. They just kind of hid the fact that it's the same line. So, we're just going to do one last one here. So if I take a look, I got some weird colors here, but if I look right here, I can go ahead with this one. I'd be tempted, okay, there's my 2. I'm going to pick another point, and I'm going to rise negative 1 and run 2, and I'm ready to go with that line. The top one is not ready to go. So I need to solve for y. So let's go advance and talk about how to do that. So the first thing would be to subtract the 2x from both sides, making a 0 pair here, and I'd have 4y equals negative 2x plus 8. They can't come together because they're not buddies. Divide by 4, divide by 4, divide by 4. The y is now alone because that's 1y. Negative 2 over 4, divide by 2, and you get negative 1 over 2x, and 8 divided by 4 is 2. And now I'm ready to graph him. But look, they're identical. So when I graph this line, it's the same line. There's 2 that are the same line, and this is called an infinitely many solutions. So today we've been talking about sort of how to solve systems of equations. I passed by the one because we had already done a parallel. So how do you do this? Let me just remind you that the first thing that you need to make sure is that both of your lines are written in y equals mx plus b. So you might have to do a little bit of transforming. A few things might need to move across the equals, and when they do, opposite sides, opposite operations. Once you have them in that easy form to graph, you graph both lines on the same piece of graph paper using a straight edge or a ruler. And then you ask yourself, where do they meet? Now I say estimate because until you check it, you're not sure if it's right. So then you take your coordinates, you put it in both of your equations, and sure enough, you'll see whether it works or not. And that's how we solve a system of equations. And we will be moving on to kind of, is there a different way other than graphing in our next video? So I hope that gets you started on solving systems, and I'll talk to you soon. Have a great day.